Jnanam Paramam Dheyam. Knowledge is supreme.
Let us continue our study of polynomials over a field, and one of the most important fact which I will state now is about the division. So we already study such property of integers in the school. So I will not recall division algorithm, what is called division. What I am trying to call now is division with remainder. So we have two polynomials f and g with coefficients in the field. K is the field, and let us assume g is a non-zero polynomial. I want to remind you again and again that we have not defined degree of a zero polynomial. So degree of a zero polynomial is not defined. Now we have given two polynomials and the g is a non-zero polynomial. Then I want to divide f by g and look at the quotient and remainder. So then the assertion is there exist unique polynomials Q and R with coefficients in K again, such that f is Q times G plus R with either R is 0 or degree of R is strictly less than degree of G. And once we prove this, uniqueness will take, because of the uniqueness, is Q is called quotient and R is called remainder. Of f by division with g. We will prove this statement, but before we prove, I just want to remind you, this is what precisely we studied in the school. If you remember, given two integers, or we started with a natural number, given two natural numbers, one of them non-zero, then we could divide the other natural number by a non-zero natural number to get a quotient and a remainder. And the remainder should, the role of the degree is played by the modulus. So the magnitude of the natural number. So either the remainder should be less than the dividend or it is 0. And this is a similar thing what we want to prove it. Instead of integers, we want to prove it for the polynomial. And as you will see, the proof is very easy. So let me indicate the proof. So proof. So proof. So we have given f and g. So let us first write g. G is b0 plus b m x power m. M is the degree of g which is this Bm is non-zero, therefore, and this is G non-zero polynomial. So degree is bigger equal to 0 and defined bigger equal to 0, and f is a0 plus a1x plus an x power n, where n is non-zero and n is the degree of f. When f is, I can write this only when f is non-zero. Remember that. Otherwise, I have no information if f is 0. So, I am going to, and we are looking for q and r. So, I am going to prove the assertion by induction on the degree of G. See, I cannot say induction on the degree of f. Degree of f may not be defined when f is 0. So, induction on the degree G. So, induction will starting, the beginning of induction should be at, so let us look at degree, not the induction on degree of f, degree of G, sorry, degree of f. So, before I should have started with this, if f is 0, then there is nothing to prove, because if f is 0, you take q equal to 0 and r equal to G. No, r equal to q is 0, then and r is also 0. Because what do we want? We are, let us write the equation what we want to satisfy. Q f should be equal to qg plus r. So, if this was 0, I will take this is 0 and this is also 0. This is also 0. So, obviously, this equation is satisfied. Q, there is no condition on Q, and there is a condition on R, that is R is either 0 or the degree of R is strictly less than degree of G. That is also satisfied. So, if f equal to 0, then there is nothing to prove, it is very easy. So, we may assume f is non-zero. So, we may assume f is non-zero. And now we will prove our assertion by induction on the degree of f. So, this sentence I should have said it here. So, by induction on the degree of f. So, f is now like this, and what do I want? I assume now the statement for the smaller degree polynomial than f, and then prove it for degree f. So, that means I want to reduce the degree of f by using the polynomial g. So, what do I do? So, I want to cancel this coefficient, and fortunately we are over a field. So, what do? You multiply G by Bm inverse, which exists because K is a field and Bm is the non-zero element of the field. So, this exists, and then I want the smaller, I want to cancel this n. So, I will multiply this by x power m minus n time. I look at this polynomial G. First of all, also I have again forgot to make a comment that if n, the degree of f is n, if degree of f is smaller than degree of G, so I will write in the side. If degree of f is smaller than degree of G, then again I will take q equal to 0 and r equal to f. Then also this equation is satisfied. So, therefore, without loss I would have assumed f is non-zero and degree of f is strictly bigger than degree of g. Should assume that. So now we are trying to cancel the top degree coefficient of f. So what do? I consider this. You remember what did I do with this? Now g as leading coefficient bm, and I multiply by bm inverse, this will become 1, and I multiply by this x power n minus m. Now that is allowed because we are assuming this is n and this is m. So we are assuming n is strictly bigger than m. So this is some positive, this is some natural number. So this, what is the leading coefficient of this, is precisely x power n, because the leading coefficient got cancelled and then this power became x power n. So leading coefficient is 1 here, and I can multiply by an now, minus an. And then subtract this quantity from f. What do I get? Let us look from the top degree, that is, this is an x power n. I want to compute the coefficient of x power n plus lower degree term. So this, from here it is coming an, from here it is coming an, bm inverse and bm. So that is an, bm inverse, bm, but then this is 0. So therefore the degree of this quantity, so let me write the result. The degree of this polynomial f minus an bm inverse x power n minus m g, this degree of this new polynomial is strictly smaller than degree of g, degree of f. Therefore, by induction hypothesis, I can apply the induction hypothesis to this polynomial. This degree is smaller, so by induction hypothesis, there exists q prime and r prime, two polynomials with either r prime is 0 or degree of r prime is strictly smaller than degree of g, such that this polynomial f minus an bm inverse x power n minus m g, this is equal to q prime times g plus r prime. This is induction hypothesis. Now I simply, what do? I simply shift this term to the other side. So that will imply, so therefore f will be equal to, shift this to the other side and take g common. So q prime plus an bm inverse x power n minus m times g plus r prime. So this is my q, the one I am looking for, and this is my r. And so this condition remains same, and on q there is no condition. So we have found a polynomial q and polynomial r with the required conditions. So this is division outcome. This is very, very important. You will see in a minute that I want to check now. For example, our problem, let me remind you, our problem was what? Our problem was given a polynomial. So given a polynomial f with coefficients in a field, we are looking for the solutions. So solutions of f in k, let us say. So solutions of f of x equal to 0 with x in k. This is what we are looking. So that means we want to decide how do you check for a given polynomial? So given f and given an element a in k, how do you check that this a is a solution of f? That means how do you check? How do we check? F of a is 0 or not? Or not? So that is, we will use now division algorithm. How will you division with remainder? So that is, so let us write in the form of corollary. So we are going to apply to this given f. So f is a polynomial in kx. A is a given element in k. Then f of a is 0 if and only if the linear polynomial x minus a divides f. But again, when you say divides f, we should better write in kx. So let us prove this. This is very easy. I wrote it on this page. इस पे लिख दिया मैंने.
नो प्रॉब्लम सर, इसका सर ये तो हो गया ना पढ़ा के सर.
हाँ ये हो गया.
तो लास्ट में प्लीज सर लिख दीजिए खाली इसको.
क्या?
ये जो चीज आप ये जो लिखे ना सर सेंटेंस एंड में, ये सर इस पे
हाँ एंड में लिख दूंगा. हाँ Okay, so let us continue with the proof. So we have now given f, and also we have given this linear polynomial, and this is my g now. I am going to apply division with remainder by dividing by f by dividing by g. Then what do we get? There exists q and r in the polynomials again, with either r is 0 or degree of r is strictly smaller than degree of g, but degree of g is 1. So this r has to have, the only possibility is r is a constant polynomial or r is 0. So this whole thing means r is constant. That means r is an element in k. K cross actually, strictly speaking. Right? So that is information. So we have written f as q times g, I will write x minus a plus r. But now I want to find what is r. Now in this equation, this is equation about polynomial, and I am going to put x equal to a. What do I get? This side I will get f of a, the other side I will get q of a and a minus a plus r of a. But r of a is r itself because it is a constant polynomial, and this is 0. So altogether it is r. So this r we have found in terms of f and a, that is f of a. So that proves that f equal to, that proves the formula f equal to q times x minus a plus f of a. This is what it proves. So when will x minus a will divide f? Precisely when the f of a is 0. So that was the content of this corollary. So division with remainder, then when we apply it again and again, then we lead to what is called Euclidean algorithm. So that is one way to find a GCD, one way to compute a GCD. If I have given two polynomials f and g, how do you compute a GCD of f and g? Okay, now when we talk about GCD, GCD means first of all remember the long form, greatest common divisor. So why should it exist? We have seen in case of integers it exists, and the method to find the GCD was to apply division algorithm again and again. So only one step we have to prove it. So prove that this is, I will put this as an exercise for you. So check that GCD of f and g, let us say f is g is non-zero. This is same as GCD of g and r. So you keep checking it like this. So you are reducing the problem to the smaller degree polynomial always. Okay, so I will not go much into this because otherwise we will not have enough time to do our course justification. I will also note here one important lemma, which is the analog of the Euclid's lemma, what we just mentioned for the integers, that says that if a prime polynomial P, capital P is a prime polynomial, that means P is a polynomial over K over a field K, and it's a prime polynomial. That means the only divisors are of the form A times P, where A is a constant, non-zero constant. If a prime polynomial P divides the product F1 to Fr, this is the product, where F1 to Fr are polynomials in K, then P divides one of them. P divides one of F1 to F1, at least one of F1 to F1. At least I should write, at least one of F1 to F1. This also is very easy to prove, so I will not prove this. Proof, check. If you get stuck, you should recall your proof for integers. That is like going back to a school. All right. So, next fact I want to again mention that this is analog again with the integers, that is a prime factorization. So recall, over the ring of integers, in the ring of integers, any natural numbers n, we can write it as either plus or minus, that is this sign, and product of prime numbers, P1 power alpha 1, PR power alpha R, where this epsilon is plus minus 1 and these P1 to PR are distinct prime numbers, distinct, and this alpha 1 to alpha R are non-zero natural numbers, bigger equal to 1. They are in n plus. I will write that notation, n plus is non-zero prime numbers. So this we have been taught in the school that every number we can divide, we can write as the product of prime numbers, and when you collect the powers of the same prime number, that is alpha 1 and so on, and it's up to a sign. And this factorization is also unique up to a permutation, unique up to plus minus 1 and a permutation of unique up to a permutation. That means what? If I have another prime factorization, then first of all the number of the distinct primes is same, sign is same, and the prime numbers, they will differ only up to a permutation. And that to avoid that, we can also put a condition that P1 less than P1, P2 etc. less than PR, then obviously it will be unique, because then there is no question of permuting. So this is a prime factorization for integers. Similarly, we have a prime factorization for polynomials. So for polynomials, what do we do? So now we are taking a polynomial f over a field. Then I want to write this f. Now that sign, remember that now come as a constant a, where a is in a field, and then product of prime polynomials, P1 power alpha 1, PR power alpha R, where these P1 to PR are prime polynomials in Kx, prime polynomials. Distinct, and alpha 1 to alpha R are non-zero natural numbers. And again, such a factorization is unique. Unique up to what? Unique up to now the elements of K cross. And now there is no way that we can say P1 less than P2 and so on. We have to just say that it is unique up to multiples of K cross and permutation. So this is called a prime factorization of f in Kx. And we know that every polynomial has a prime factorization. That I am going to assume that. But please go back and check all these things. Best way to check is recall your proofs for ring of integers and then write the analogues of the polynomials in one variable. Now the next step, it's clear what I am going to do is, among these prime factors, I will look at their degrees and I will order them according to the degrees, degree 1, degree 2, degree 3 and so on. And therefore, what will I do? Among them, I will write the linear ones first. First of all, before I write that, we have already also information about the degree. So degree of f will be equal to sum of degrees of the pi's, I from 1 to r, and also the alpha 1, alpha i's, you have to multiply by alpha i's, because the degree of p power alpha in general equal to alpha times degree p, and then the degree of the product you apply repeatedly, that will be this formula. Now among the pi's, I want to take out the linear ones first. So f will look like then a, and first I will like few linear ones, so that is x minus a1, x minus as, and then remaining ones now I will number them as q1 power beta 1, qt power beta t, where now degree of qj's is strictly bigger than 1. Linear polynomials, they will look, maybe they will have coefficient of x here, but I am going to multiply all the inverses and I will absorb in this new way. So if what I am saying is following, if the linear polynomial looks like this and I want to make it in this form, then I am going to multiply this polynomial by a inverse and change the write this b as minus b prime, and then absorb this a prime, a inverse also here. So this all together will become x minus b prime. So all the linear polynomials I can write in this form, and all these inverses they will get absorbed in this a. There are some other letters, right? So therefore in any case I will reform given f into this one, and these are the degree 2 or more polynomials. So obviously now what we know is all these AIs, all these A1 to AR, they are precisely the solutions. S, these are solutions of F. And these Q's, they will not have, because I try to take possible. So let me just summarize what we have done in this lecture today. At the end, given polynomial f with coefficients in a field, we have decomposed into prime polynomials. Some of them are linear, some of them are not linear, and the linear polynomials will precisely give the solutions of f equal to 0 in the field K. So next time we will, starting from here, we will go on to study solutions of a given polynomial over a given field into a larger field. So this is a big project, and we will slowly get into the subject. How do we find all solutions, and whether is it possible to have formulas for them or not? That is our main concern. Thank you very much.